In this final video in the oscillator module, I'm going to treat the case of a damped oscillator that's driven by a periodic but non-sinusoidal force. So the situation is the same as previously. We have an oscillator with a restoring force, a damping force, and a driving force. From this motor, it has some explicit time dependence that gives us this differential equation by applying Newton's second law. And what we're doing different this time, as I said, is the fact that we're saying that this force is periodic. In other words, f of t equals f of t plus tau, where tau is the period for all times. But it's not sinusoidal. Okay? So that means that the solution that we have used before, which is given a sinusoidal driving force, have to be modified somewhat. Luckily, we can make use of Fourier series analysis, which has a couple of math interlude videos for you to review. Basically, we know that if we have a periodic function, then we can write it on the following form, right? This normalized force here, f of t, can be written as follows. So we can say that this force consists of a fundamental wave here that oscillates at the frequency of the driving force, omega, where omega is 2 pi over tau. So this first Fourier component is known as the fundamental, and it oscillates at omega. And the higher ones, they are known as overtones. So the first overtone oscillates at 2 omega, the second one at 3 omega, etc. They all oscillate at multiples of the fundamental, so that in general, the nth overtone oscillates at frequency n omega. A good illustration of this comes from the Wikipedia page on Fourier series. We have this particular animated GIF, which shows a wave here, and you can decompose that wave onto its sinusoidal components, like this. It's equal to the sum of all of these, which you can find through Fourier series analysis, and you just sum them all together to get this wave. And what you have plotted here is what's known as the spectrum of the signal. We have frequency increasing towards the right, and then we have the relative amplitude of all the Fourier components here. So the fundamental is here, then this is the amplitude of the first overtone, the second, the third, the fourth, and the fifth overtone. And then we just return to the original waveform. Okay, but you already all know all of that. Now we're going to use this decomposition in order to solve this differential equation. So we previously said that we can write this differential equation on a simpler form. We can just say that this is just d acting on x of t equals f of t, where d is this linear differential operator. Okay, so if we have that, then we want to be able to solve this. Now, because we can do the Fourier decomposition here, we can also write that f of t is equal to the sum of n goes from 1 to infinity of fn of t. So this first one here, this is f1 of t, that's the fundamental. This is f2 of t, f3 of t, etc. So the equation that we really need to solve is the following, right? But that still doesn't help us too much. But in order to, there's supposed to be an n here, but in order to make this a little simpler, we're going to first solve a subset of this equation. We're going to solve the following. So we just look at the nth component of the Fourier series, and we solve this equation equal to the nth component of the Fourier series. So that's the force we pretend. Of course, we already know what that is. It's f(0n) times cosine of n omega plus this phase there. And we already have the solution to that, because that's the case of a driven oscillator, or a damped driven oscillator with a sinusoidal driving force. So sinusoidal driving force. So that means that we can say that x of n of t is an cosine of n omega plus phi n minus delta n. I'm going to have to move this in order to have space for everything. Where a sub n, and I'm going to write this as a square. Okay, so like that. So each of these sub-solutions for each of these waves here, for each of these Fourier components, has the same form as it did previously. The only difference now is that instead of oscillating at a frequency omega, we're oscillating at a frequency n times omega. Otherwise, the amplitude and the phase look exactly the same. So now, because this equation is linear, because this differential operator is linear, we can say that if we sum up all of these together, all these solutions together, the differential operator acting on a sum of these will be equal to the sum of all the f sub n's. So we have a linear equation. Right. If this is true, then this must be true because the equation is linear. But that's just equal to f of t, of course. So that means we've actually already solved the equation that we were looking for. So we have that the solution, x of t, is just the sum of this, of all the partial solutions. Okay, this is the solution, with the caveat that the transients have died away, and that's something we have to mention, that the time here has to be much greater than 1 over beta. Now, we spent a couple of videos deriving the properties of this amplitude an, and one thing that we found was that it strongly peaked, of course, near the resonance, where omega naught is equal to, in this case, n omega. And that's the case here now for all of the terms of the sum. So the a of n is strongly peaked at omega equals omega naught over n. So that's just a little bit different from before, right? We have a peak whenever omega is equal to omega naught divided by an integer. So for instance, if we want to, so what happens when we lower the frequency is that the overtones one by one become resonant with the oscillator. So if omega equals omega naught, then the fundamental, this term, becomes resonant with the oscillator. If we halve the frequency, then now the first overtone will become resonant with the oscillator. And if you go to omega equals omega naught over 3, then the second overtone, which oscillates at 3 omega, will become resonant with the oscillator at frequency omega naught. So what we have here is a case where all the overtones can excite the resonance. And I have a little Mathematica file on this, but before I show that to you, I'm going to make one more calculation, and that is of the Rms displacement. The motion of this oscillator is in principle pretty complicated, and in order to better understand it, one way we can characterize it is through its Rms displacement. That tells you roughly how much it moves away from its equilibrium, whereas there's no overall amplitude because we have all these a's each multiply their own cosine function. But we can calculate the Rms displacement, which, as you should know, is equal to the square root of the average of x squared. Right? So in order to calculate x squared, or the average of x squared, we just have to take the integral over one period and normalize by the length of the period of x of t squared dt. And that's what we need to calculate. Now we know from the previous video and also from Parseval's theorem that we can write this as the scalar product of x of t with x of t, viewing then this time dependence, this function, as a vector. And this is now going to be equal to 1/2 the sum over n goes from 1 to infinity of a sub n squared. And this is due to Parseval's theorem. And if you don't know Parseval's theorem, I urge you to review the second Math Interludes video on Fourier series. Okay, so that's easy enough to calculate, right? We already know what all these a's are. A sub n's are, it's given here. And then we can calculate the RMS amplitude just by summing up their squares. This also gives you an idea of what the energy of the system is like, because remember, for a sinusoidal oscillator, the energy is proportional to the amplitude square. The same thing is true here. So the energy is actually proportional to this value here. Okay, so if we were to plot x squared as a function of time, we can get an idea of how much energy is contained within the oscillator, even though it doesn't oscillate at a single frequency. Physically, this relationship means that the response of the oscillator, in an energetic sense, to a non-sinusoidal driving force is just equal to the sum of the response to all the Fourier components. But you have to square here, so you have to think about it in an energy sense. So, in other words, So the response of the oscillator to a periodic force equals the sum in an energy sense of the response to all the harmonics of the force. Okay. So as a final part of this video, I'm going to show you the Mathematica program that I've written to illustrate this point. So this is it. So let me explain all the pieces here. We have over here a choice of 7 different periodic functions. This is a plot of that function. This is the force, right, f of t, that's being applied to the oscillator. Over here, x of t, we have the response of that oscillator, and since that can vary in amplitude, I can change the scale here in the y direction. And this is the RMS amplitude of the oscillator for the particular period that we've chosen. So this slider over here changes the period of the oscillation, so that if I pull it to the right here, then the period gets longer and longer, a slower and slower oscillation. Q is the Q factor of this oscillator, and I can vary that from 1 to 20 with the setup. Okay, so let's see what happens here. This is really just a case of a single resonance, just like what we've seen before. So we start at a low frequency, then we get a small response here of this oscillator. And then that response will grow as we approach resonance. And when we are on resonance, the response is at its strongest. And then when we are now increasing the period, that is reducing the frequency, we get a smaller and smaller response. So this is just like the previous Mathematica program. The only difference here is that I'm sliding the period instead of the oscillation frequency. So as I'm moving to the right, the period increases and the frequency decreases. So this is a sinusoid. There's one single resonance there. Okay, let's pick a square wave. This is a square wave, right? So we can see there's a small response here at this particular frequency. We have a high frequency, a small period. And I'm going to now increase that period so that it matches the, as close as I can, period of the natural period of the oscillator. And then we get a large response here, but it's sinusoidal, right? But it's at the same frequency as the oscillator. And then I'm increasing the period of the driving force, and you can see that it reduces the period, and nothing happens until the period becomes 3 times the period of the natural frequency of the oscillator, or 3 times the natural period of the oscillator. So you can see here that now the oscillator is oscillating at the same frequency that it did when we had our driving force tuned to this period. So what's happening here is that the second harmonic of this square wave is exciting the oscillator at a higher frequency. And we can keep going until we go to the 5th harmonic, which is the 4th overtone, and again we get the same frequency excited, and in between we have relatively little excitation. And we can do this for other waves as well. This is the triangular wave, and we can see here we have a resonance, another resonance at 3 omega, or at 3 times the period, and yet a smaller one at 5 times the period. This is now at a Q of 5. I can change the Q. Higher Qs means that all the resonances become sharper and higher. And smaller Q means that the resonances become wider. Right. So then I can pull this around here. Let me increase the sensitivity here, right? So what we have is that the response of the oscillator is not exactly the same as the as the force that you apply to it, but it tries to get close in any case. So here we can see when we are away from the resonances, the response tries to emulate what we have here. So you go up and then down, up and down. It's sort of about right. And here we go up and down once, up and down once. Right. And we have all the other functions that you can play with here. So this is the this log function here. It has more peaks because, as opposed to the square wave and the triangular wave, it actually has harmonic content at the second harmonic, the first overtone, and the third overtone, the fourth harmonic. Okay. So as usual, I'll include this in Canvas for you to play with to get a better idea of, to get a better feel for how this works. But otherwise, this ends the module in oscillations. And next, we are going to introduce a whole new branch of calculus, the calculus of variations, which we will need in order to introduce Lagrangian mechanics, which is going to be the core of the rest of this course.